11 months after it disappeared, Zach managed to find Ceres very close to the positions I had predicted.
And the amazing thing is that this was actually against the predictions by leading astronomers at the time, including Zach himself. In this video, you're going to see a conversation with the 19th century mathematician Carl Friedrich Gauss. Most of the content for this video comes from a book called Gauss, a biographical study by W.K. Buhler. In this video, we're going to go over a lot of topics, starting with math. The mathematical concepts are going to get fairly dense, I should warn, despite my best attempts to explain some of them. If you're finding that the math in this video is not something that you're able to follow along with, then I highly encourage you to go ahead to the sections on astronomy, on cartography, on one part where Gauss is mapping the entire region of Germany, on physics. I encourage you to go ahead and skip there if you want to. We're going to cover Gauss, some of his relationship with contemporaries like Bolyai or Legendre, and even Jacobi. So without further ado, please enjoy this conversation, and now I bring you Carl Gauss. Welcome everyone. In this video, I'm speaking with Dr. Johann Carl Friedrich Gauss. Professor, it's an honor to have you back here.
It's my pleasure. It's good to see you again, Kareem.
All right. Now, Dr. Gauss is widely regarded as quite possibly the greatest mathematician in history. I mean, his unthinkable contributions include a large chunk of number theory laid out in his masterpiece, Disquisitiones Arithmeticae, predicting the orbit of Ceres, which we'll get into, contributions in physics, in magnetism, and so much more. I mean, honestly, one just has to pull up the Wikipedia page of concepts and phenomena named after Gauss to see what he did. I mean, look at that. It's incredible. And I'm not going to repeat the anecdote of you summing the... Okay, I will. See, the short version of the story is that when Gauss was a boy, the teacher wanted to punish the class. And so what did he do? He said, sum all the numbers from 1 to 100, thinking it's going to take them forever. Now Gauss just immediately blurts out 5,050, and the teacher's like, how did you come up with that right on the spot? And Gauss is like, well, okay, if you take the numbers like this and do 1 plus 100, it's 101. If you go in, 2 plus 99 is 101. 3 plus 98 is 101. And so it's 101 times 50, so 5,050. I think we can at least start with the masterpiece, which is Disquisitiones Arithmeticae, including number theory and linear algebra. So, Professor, please tell us about your great work.
Well, I dedicated it to the Duke of Brunswick for sponsoring my education and career. You'll see that it is organized into 7 sections. The first 3 are introductory, and the next 3 are the core, mainly covering number theory. There is an additional 7th section which is dedicated to an unrelated topic. It is what you refer to as cyclotomic polynomials. So, in the first section, we begin with elementary concepts of number theory, such as congruence for rational integers modulo a, natural number, and residue, and elementary properties pertaining to...
Sorry to interrupt. I just want to define some of these elementary concepts here. According to Whitman College, congruence is in number theory. I'm reading here. We say the integers a and b are congruent modulo n, and write a congruent b mod n if they have the same remainder on division by n. Oh, yeah, so we divide both numbers by n, and if they have the same remainder, then they're congruent. Hopefully I'll have something on the screen demonstrating this for listeners. And hold on here. On the website, they go on to say this notation and much of the elementary theory of congruence is due to the famous German mathematician Carl Friedrich Gauss, certainly the outstanding mathematician of his time, and perhaps the greatest mathematician of all time. The other concept you mentioned, which I want to define, is residue, which, according to the University of Washington, the residue of a modulo m is the unique integer r to which a is congruent modulo m. Okay, so an integer can be congruent to several others, and the residue is just one of them, which is not greater than the modulus. So out of the congruent integers, it's a unique one. Sorry, Professor, is there anything else in section 1? Please continue.
I shall continue with section 2. Here I prove the uniqueness of the factorization of integers into primes and define concepts such as greatest common divisor and least common multiple. I provide an alternative to the Euclidean algorithm for solving the equation. ax plus t is congruent to c. In section 3, I investigated the residues of a power of a given number modulo odd primes. I provided 2 proofs of Fermat's little theorem, both from previous mathematicians. One by exhaustion, which goes back to Euler, perhaps even Leibniz, and one using the binomial theorem.
I'm pulling up Fermat's little theorem here. It says that, as you can see on the screen, a to the power of p is congruent to a mod p. Is there anything else in section 2, de residuis potestatum?
Well, the binomial theorem's proof leads to the notion of a primitive root. This is where the powers a squared, a cubed, and so on mod p all yield integers relatively prime to p. Using this concept, I gave a relation which I ask that you please provide to the viewer. In this relation, a is a fixed but arbitrary primitive root mod p. This theorem was already known by Euler and Lambert, but I believe that I was the first to rigorously demonstrate that primitive roots exist for a prime n. The proofs I gave were a non-constructive existence proof and a constructive one.
Right, so we're continuing here with modular arithmetic. And I do want to repeat again, if you're not familiar with number theory, there's plenty of other sections here, including astronomy that we're going to get into. There's geodetic mapping, physics, magnetism, which should be much more accessible. In this book, one of your main contributions was a proof of quadratic reciprocity. I'll have it up on the screen. You can see it uses the Legendre symbol. And according to Wikipedia, it lets us determine whether there's an integer solution for any quadratic equation of this form right here for an odd prime p. Okay, so how did you prove it?
Oh, well, I didn't use the term quadratic reciprocity. In section 4, I describes the law as theorema fundamentale. That is, the fundamental theorem. The theorem itself was originally formulated by Euler and discussed by Legendre at length, but without a correct proof. My first proof starts with showing that the law holds for selected primes. Then I generalize with complete induction over the primes.
Yeah, I mean, I love how even Euler himself couldn't prove it, and then you just come up with 6 proofs because you can.
Well, I wanted to demonstrate the theorem's depth and beauty from various perspectives. I did also credit Euler and Legendre because my work clearly built on theirs.
Right, yeah. So what came next?
Well, after proving what you call the law of quadratic reciprocity, I solved by factorization the problem of determining for 2 arbitrary numbers where one is quadratic residue modulo the other. I also give a construction of linear forms containing all primes, which are or are not quadratic residues of a given number.
And I think that the most substantial part of your book, in the eyes of many, is actually the 5th section where you deal with the theory of binary quadratic forms. Those are polynomials that look a bit like this on the screen. Yeah.
Yes, I give a transformation law for forms. If a form can be transformed into another by a substitution of integer coefficients, then one form is contained in the other. What that means is that the discriminant of the second divides the discriminant of the first. I also define equivalent forms whereby both contain each other.
All right, yeah, that's quite a bit to digest there. By the way, we do have a video here where we explain some of these concepts, including discriminants, with Dr. Gauss himself. So if you're interested in that, I recommend that you check out that video. Professor, please continue.
Well, I showed that each class of properly equivalent forms with a given discriminant can be represented by a form called the reduced form, and I provide algebraic characteristics of such forms. I conclude with theorems which describe the transformation of equivalent forms into each other, which leads to Pell's equation.
All right, and were these results already known during your time?
Oh yes, Pell's equation in particular had already been investigated by Fermat, and the results provided until this point in section 5 had been proven by Lagrange. With regards to original results, I investigate orders, such as primitive and properly primitive. Then I go into the classification of orders into genera and the composition of forms, that is, classes, orders, and genera.
Right, and your book also deals with the theory of ternary form, which we need to calculate the exact genera for a given form. So what did you find on this topic?
I start with a derivation of elementary transformation properties. I define equivalent forms and go into equivalence classes of ternary forms. In this section, I demonstrate the representation of binary bi-ternary forms.
Okay, and what exactly were the applications of this?
One of them is proof of Fermat's statement about the decomposability of an arbitrary positive number into a sum of 3 triangular numbers. Another is that every integer can be represented as the sum of at most 4 squares.
And actually, I think a lot of people will realize that this work on ternary forms was a major contribution because this later became its own field and was investigated by people like Dirichlet, Eisenstein, H.J.S. Smith, Minkowski. So we're nearing the end of this masterful work with just sections 6 and 7 to cover. Professor, please continue with section 6.
Section 6 pertains to applications of section 5, such as partial fractions, periodic decimals, and the resolution of congruences by my exclusion method.
Right, and I think the most popular part of your work actually is section 7. For example, Abel himself derived huge concepts from your generalizations of the division of the square, which correction circle, which we now call cyclotomy. And here we actually get into your famous proof, which had been investigated since the time of the Greeks, which is constructing a 17-gon with just a compass and a straight edge. Apparently this was actually a very difficult concept that a lot of people weren't even sure was possible. So, Professor, please give us your take on this.
Actually, I solved it for the general case of an n-gon for a prime number greater than 2. I used primitive roots and a manipulation of the way the coefficients of a polynomial can be expressed as functions of its roots.
Right, yeah, it's a bit hard to visualize, although I think that what people can appreciate, though, is that this was just how difficult of a problem this was and how long this had stumped mathematicians. Now, a book of this magnitude and importance already puts Gauss into the upper echelon of mathematicians throughout history. But as we can see, if we, on that Wikipedia page, I mean, we've barely scratched the surface, not just in mathematics, to say less of like physics or cartography. But that, of course, even this is not an exhaustive list of your mathematical contributions. Professor, please take us to another mathematical concept which you investigated, which we now call Gauss sums.
Yes, the 1808 paper, which you implicitly referred to, is Summatio Quorundam Serierum Singularium. In English, that is summation of certain singular series.
Yeah, and sorry to interrupt, But for contemporary audiences, the singular series, those are the actual Gauss sums. That's what he called them. Anyways, please continue.
The actual objective in the paper was to determine the signs of certain expressions, which I had not been able to solve in Disquisitiones. Working on the problem was rather infuriating because of what I was able to prove rigorously without being able to determine the signs. Hardly a week went by in 4 years without one or more unsuccessful attempts to unravel this knot. I succeeded only by the grace of God, and it came like lightning.
Wow. Yeah, I think that this is actually a good lesson to the students out there that even the greatest mathematicians throughout history, the results don't come easy. And you mentioned 4 years of working on a problem. Like, I can't even imagine like 1 year working on a problem. It's just unfathomable. All right. Let's discuss another work here, which I think is very important, which is actually your dissertation, Dr. Gauss, in 1799, which I'm going to read the title here in English, which I will warn you guys about. A new demonstration of the theorem that every rational algebraic integral function of one variable can be resolved into real factors of the first or second degree. Okay, that's quite the title, but for contemporary students, what this actually is the fundamental theorem of algebra. So this is a theorem which I should have on the screen, which tells us that a polynomial of this form is going to have exactly n roots. And I may leave a link to Khan Academy's explanation of it because I think that they do a great job. Credits to Sal there. But Professor T, please tell us about this concept of the fundamental theorem of algebra from your dissertation.
Well, in 1798, I moved back to my hometown in Brunswick. The Duke there had sponsored my education and had requested the completion of a dissertation. This is, of course, the same one to whom I dedicated Disquisitiones Arithmeticae. Herein I provided 3 proofs, the first and last being very similar to each other. The third proof is analytic, where I use Cauchy's integral theorem by considering for the polynomial f, the expression that I trust you will display for the audience vanishes if x does not have a root. The second proof uses algebraic properties and a differential equation between the initial polynomial and its discriminant.
Yeah, and I mean, the importance of this theorem cannot be understated, or overstated, sorry. I mean, if we look here, I'm actually, according to ChatGPT, the fundamental theorem of algebra, it establishes the relationship between algebra and complex analysis. It shows that the field of complex numbers is algebraically closed. And another thing is that a lot of equations and problems in engineering, they depend on this theorem to basically guarantee that there is a solution to the problem. But I think that's enough mathematics for now. Let's go over to some of your contributions in astronomy because, Professor, I believe that this was not just a hobby of yours. This was an actual occupation of yours for a long time. And one of your greatest discoveries here, which I just can't fathom, is your prediction of the orbit of Ceres, which, for those who aren't familiar, Ceres is a dwarf planet that orbits between Mars and Jupiter. In fact, it's actually the largest object in the asteroid belt. Professor, could you tell us about this amazing prediction of yours?
In Göttingen, I was in contact with the professor of astronomy, Seyfer. In my studies of the classical literature, I had become acquainted with the mathematical problems pertaining to astronomy, namely the computation of the orbits of celestial bodies. The situation was such that in 1781, Uranus was discovered and the first reliable sky maps were compiled. This was groundbreaking for astronomy because we finally had the data needed for precise calculation of the perturbations of the planets.
Right, yeah, perturbations, of course, meaning that, like, for example, the orbit of Uranus doesn't just depend on the gravitational pull of the sun, it also depends on the gravity of Neptune is also pulling on Uranus. So they both have to be taken into account. And of course, if I may add, state the obvious, I mean, we're talking about the 1800s. There's obviously no Hubble Space Telescope. Not even radio telescopes had been invented at that time. The observations were scarce and inaccurate. And in fact, like planet Neptune was only discovered in 1846, which is very late into Gauss's
Exactly.
life, right?
We had the mathematical tools for this task earlier, but now, after the discovery of Uranus, we had the necessary data. There was an observatory in Seeburg, and I was in correspondence with its director, Zach, who was also the editor of the main astronomical periodical Monolithic Correspondence. Ceres had been discovered by the Italian astronomer Giuseppe Piazzi in January 1801. We had observed only 9 degrees of its orbit before it vanished in the sun's glare just 41 days after its discovery. Later in the year, it became obvious that it should be visible again, and I had made a prediction based on an efficient method of orbit determination I had created. In December, a year after Ceres was discovered, and 11 months after it disappeared, Zach managed to find Ceres very close to the positions I had predicted.
And the amazing thing is that this was actually against the predictions by leading astronomers at the time, including Zach himself. And the other thing to note is that it's very difficult to predict an orbit with so few observations, just 41 days. And like Uranus, for example, had numerous observations. And the other thing is that its orbit follows a fairly clear circular path, whereas Ceres, again, just 41 days. And the orbit itself was not that circular or easy to predict. So, I mean, it's incredible. And this was the start of your amazing career as an astronomer, which can't be separated from your role as a mathematician, given how much mathematics you used in, for example, predicting these orbits. But now let's go ahead and discuss another major project of yours, which was in, I believe, 1818, the geodesic mapping of Hanover, which is a region of Germany. I'm not sure if it's still an actual state in Germany. The thing is, mathematicians will count you as one of the greatest mathematicians of all time. And then astronomers and physicists will claim you as one of their greatest. But even mappers, surveyors will count you as one of their greatest. So how did the geodesic mapping of Hanover play out?
This took place between 1818 and 1832. The techniques for surveying were rather simple. The area to measure had to be covered by a grid of triangles whose vertices were visually connected. We then used trigonometry to measure distances. The lengths of one side of every triangle had to be measured precisely. A certain part of Hanover had already been measured during its occupation by Napoleon, but even this was insufficient. One of the major challenges was that the kingdom's topography is flat and is covered by vast forests. During the summer months of these years, I rarely spent a night in my own bed and was often in one place only a few nights at a time, because it would have been too inefficient to regularly commute to the surveying site. Here I invented a device known as the heliotrope, which is an instrument with movable mirrors for reflecting sunlight. We used these over vast distances to mark triangulation positions. It was an arduous process. Many times I doubted whether it was at all possible. Trees had to be cut down to finish connections between points, often in hilly and difficult terrain.
Yeah, I mean, and can you imagine just doing this without any drones? Even hot air balloons had not even been around at that time. Just to get out of the way, so the way that this did work, as Professor Gauss alluded to, is that you have to create these triangles, and then you can use trigonometry to get certain data on them, like the area and distances. And so doing this, not even radio had been invented, no walkie-talkies to like tell people your position, no trucks. Again, no, he couldn't just commute to his home and then back. Professor, how long did this take?
Regretfully, it did consume a good decade of my life. But during this time, I also published the paper Determination of the Difference in Latitude between the Observatories of Göttingen and Altona. I used the method of least squares extensively in my surveys and developed the theory of conformal mappings. In this paper, I also determined the oblateness of the Earth using least squares.
Yeah, 'cause, I mean, why not? Like, might as well casually calculate the oblateness of the Earth down to, what, 5 decimal places? Yeah, and I think that all of this gives us a good transition to your contributions in geometry. You see, at that time, if I understand correctly, the principal problem was the Euclid's fifth axiom, which, for those unfamiliar, I think I'll have a TED video linked, which explains this much better than I can. But there were a lot of attempts at the time to derive this fifth axiom from either from the others or to prove that it was just an unrelated assumption. Please tell us about your work with the Hungarian mathematician, one of your contemporaries, Wolfgang Bolyai. Original name is Farkas Bolyai. What did you guys work on in geometry?
Yes, Bolyai was a good friend of mine since Göttingen. We both tried to solve the problem with geometric constructions that avoided the axiom of parallels. In 1804, he sent me a letter where he claimed that Euclid's fifth axiom was not independent and that it could be deduced from the other Euclidean axioms. I mentioned that this proof was false because of an unjustified assumption he had made. However, I had for a very long time believed that this axiom was an assumption and that other non-Euclidean geometries could arise by making different assumptions.
Right, and like nowadays, non-Euclidean geometry is pretty well established. I believe it's actually called hyperbolic geometry. And in fact, your friend Wolfgang's son, János Bolyai, was a big pioneer of this, along with an unrelated mathematician in Russia, Lobachevsky. Is that right?
That is correct, yes. When the young Bolyai discovered that Euclid's axiom was indeed only an assumption and did not follow from his other postulates, and could be used to create non-Euclidean geometries, his father sent the results to me. I did point out to the Bolyais that I had already worked on this, although I had kept these insights I had into non-Euclidean geometry private. I had believed it to be a far too controversial field to publish in. But on the topic of non-Euclidean space, one concept which I was fond of, despite its infancy and controversy, is its inclusion of an absolute length. However, this discussion of non-Euclidean space was to me an irrelevant philosophical discussion when the real world clearly seemed to be in accordance with Euclidean geometry.
Okay, so you say that you were at least aware of non-Euclidean geometries, but you did publish a fair amount in geometry regardless. Like in 1823, I'm looking here, you submitted a paper to the Danish Academy of Sciences called the Copenhagen Prize Essay, which, I mean, here we're dealing with cartography, so projecting a sphere onto a plane to get maps. And I believe the goal of this prize essay was to get all possible projections that you could use to create a map. So could you tell us a bit about this?
Yes, you see, the problem of projecting a sphere onto a plane had generally already been solved by Lambert. Previously, stereographic projection maps had been available since antiquity. So too was Mercator's mapping. In my essay, I derived a conformality criterion for mappings between two arbitrary areas. I used integral transformations to reduce the square of a line element to a form familiar from the investigations of Euler and Lagrange.
Right. Yeah, there's a little bit of terminology here. You said that you derived a conformality criterion, which, like if we pull up conformal maps on Wikipedia, it says it's a function that locally preserves angles, but not necessarily lengths. So, like if we look at the Mercator projection that, is very common in like classrooms, you see that, for example, Greenland and Antarctica are ridiculously huge, but they are actually in the correct shape. So, my understanding of it is that like the angles there are correct, but the like scale and size is wrong. So would the Mercator projection that we see here be an example of a conformal map?
Indeed it would. You see, the Mercator projection is one example of a conformal map. But I derived a general conformality criterion which would allow us to determine whether two locations are conformal. That is, whether they preserve angles. I started with the similarity condition that all infinitely small lines which start in one point of the first area and are entirely contained in it are proportional to the corresponding lines in the other area. And secondly, that the former have among themselves the same angles as the latter.
So you're making the case that if we take a globe and a hypothetical map, and we take, you said infinitely small lines on the sphere and their corresponding areas on the map, that they're just being scaled. That is, like they're still proportional to each other. So that would imply, as you're saying, that there's a scaling factor between those lines?
Yes, precisely. However, the angles remain identical. This means that the surfaces are locally similar in their intrinsic geometry, even if their embeddings in 3D space might differ.
All right. That's interesting insight into cartography. Now we already went over Disquisitiones Arithmeticae from number theory, but there's actually another work with not to be confused with it, Disquisitiones Generales, which is actually on differential geometry. So could you talk a little bit about Disquisitiones Generales?
Yes, I developed the basis for an intrinsic differential geometry. This one was inspired by astronomy. In this work, I defined my theorema egregium, in English, remarkable theorem, which states that the curvature of a surface in 3 dimensions depends on distances measured on the surface itself and not on how the surface is embedded in 3D space. It is an intrinsic property that can be measured using values on the surface, regardless of what environment it is in. Previously, it was thought that curvature was an extrinsic property tied to how a surface sits in 3D space.
Right, yeah, and just for anyone watching, so intrinsic and extrinsic, the difference is that an intrinsic property is something like where if we have a line, it doesn't matter if the line is in 2D or 3D or 4D, it's always the same length because the length has to do with the line. It has nothing to do with the space. Whereas if I take, let's say, a normal vector coming from, let's say, this mug here, we have a vector here coming this way in this direction. It depends on the fact that it's in 3D. It's different depending on the space. So that would be an extrinsic property, the normal line. So yeah, that's intrinsic and extrinsic properties. Professor? What did your curvature formula allow you to calculate?
Yeah, so my curvature formula allows you to calculate the curvature of a surface based on measurements on the surface itself, such as lengths, angles, and areas of small triangles.
Right, and actually, apparently, these theorems here that you helped develop are now a large part of how we come to understand the universe. Because you see, there were physicists that came after you, Professor, like Albert Einstein and Hermann Minkowski, who developed a theory called general relativity, which actually used your work on curves to give us a theory that actually surpassed Isaac Newton's laws in many respects.
This is very interesting. Can you please elaborate?
Well, you are familiar with your contemporary Bernhard Riemann, correct?
Of course, he was my student at Göttingen and helped make incredible advances in the differential geometry we have just discussed.
Right, and so he took your concepts of curvature and generalized it into higher dimensions, as you know. But unfortunately, I'm not completely familiar with the mathematical details behind general relativity. But from what I understand, it says that space and time are a curved four-dimensional manifold. So it would not have been possible without your work on curves and Riemann's extension of it, because that allowed these later physicists to then describe space and time as curved in four dimensions.
That is certainly interesting. See, I was Riemann's mentor while he completed his groundbreaking doctoral dissertation. I had known that this would lead to major advancements in differential geometry, but had not considered that this could be related to the nature of universe. A welcome surprise, I suppose.
Oh, yeah. And actually, the measure of curvature, which you also state in Disquisitiones Generales, is now called Gaussian curvature. So we have Gaussian curvature, the Gauss lemma, Gauss sum. Is there anything else you would like to add from your differential geometric work in Disquisitiones Generales?
Yes, I think it's important to know that my later results deal with the properties of certain geodesics, which are the shortest paths on a three-dimensional hypersurface. In the summary of my work, I note that the total curvature of a geodetic triangle is equal to the amount by which the sum of its angles exceeds 180 degrees. This was later elaborated on by Pierre-Ossian Bonnet, who published a special case of it in 1848. It states that the curvature of a geodetic triangle is equal to the amount by which the sum of its angles exceeds 180 degrees.
Yeah, let me go ahead and pull up what a spherical, or actually, as you called it, a geodetic triangle is. You can see that they're formed by three lines on a sphere. And so we know that in a regular triangle, when you add up all the angles inside, it equals 180 degrees always. But you're saying that in one of these spherical triangles, the sum of the angles exceeds 180 degrees, and actually the amount by which it exceeds 180 is actually the curvature of the surface. Did you apply this anywhere?
Actually, during my surveys of Germany, I created one of these triangles which was between Brocken, Hohenhagen, and Inselberg. This was an extremely large triangle, covering vast space.
Yeah, actually, let me go ahead and quickly check that here on Google Maps. Oh my god. Dude, this is huge. Like, just Brocken to Inselberg, that's already 106 kilometers, so like 65 miles. Wow. Please go on.
I was seeking to understand what the effect of distortions were on my calculations using two-dimensional triangles. Distortions such as the curvature of the Earth's surface and variations in topography such as hills, valleys, and such like.
Okay, was there any actual distortion by this?
I know not any noticeable distortion that would require using geodetic triangles instead of simple two-dimensional ones. I had suspected this, but I believe that it is in the nature of the scientist to understand and check these irregularities.
Yeah, I think that makes sense. And according to Gemini here, it takes about 69.17 miles until you get just 1 degree of curvature. But I think it's only natural that we also discuss your actual contributions to physics itself. So what did you actually write on physics?
I wrote a paper in 1829 called On a General Fundamental Law of Mechanics, which was a very theoretical work. It is related to D'Alembert's principle of virtual dislocations. Here I derived a new principle of mechanics, the principle of least constraint. The basic assumption of the paper is that any movement of a mechanical system at an arbitrary moment is in maximal agreement with the free movement. That is to say that minimal constraints always prevail. This allowed me to unify my treatment of static and dynamic mechanical problems.
Yeah, okay, let's go ahead and digest this. So virtual dislocation shows how the mechanical system's trajectory can deviate from the, how it can hypothetically deviate very slightly from the actual trajectory of the system without violating the system's constraints. Professor, do you think you could give us an example of this, make it easier?
Certainly. Consider a double pendulum consisting of two masses. If there were no constraints, the two masses would experience free accelerations based on the forces acting on them, such as gravity. The rods introduce the constraints that the distance between the rods are constant. They are free to move in all different directions, but they cannot move farther than the rod allows. The actual accelerations of the masses will differ from the unconstrained accelerations. So based on this equation, the accelerations given as r1 and r2 minimize this function.
Yeah, and I should have something up on the screen to help people see what this really is. And this actually does have a lot of usage in areas where Newton's laws become a bit cumbersome, and this is a bit of a shortcut to get easier results there. But I believe you also published another work on physics in 1829 called Principia Generalia. Is that correct?
Yes, of course. It is not as fundamental and is only concerned with theory. So no experiments were performed here. One of my objectives here was to show how much mathematics can contribute to the elucidation and explanation of nature. The paper is a discussion of the forces of attraction, molecular forces which are effective over small distances and by which capillary phenomena can be explained.
Yeah, and capillary action is referring to the process of a fluid or liquid flowing in a small tube in a narrow space without the external assistance of gravity. So you can actually try this yourself. If you put a straw into a cup, then you'll notice that the actual water level in the straw is higher than in the cup. And what's actually going on here is that the capillary action, the force, is that the walls of the straw are attracting water to the walls of the straw, which is causing the water to rise. And this is actually how plants transport water to their stems against the force of gravity. Is that right?
That's correct, yes. So Laplace developed a theory on this before me. I introduced my work with the observation that Laplace's theory on capillary pressure depends on two fundamental assumptions. Namely that a certain differential equation describes the equilibrium of a fluid, and that in equilibrium, the free surface of the fluid touches the wall of its container at a certain angle. Laplace derived the differential equation, but his second condition, that the fluid's surface touches the wall of the container at such an angle, that this was an unproven assumption. I sought to derive Laplace's results in a rigorous manner. The way I did this is by using my principle of least constraint to virtual dislocations.
Right, okay, so Laplace assumed that for a fluid in a tube that the parts of the fluid touching the wall will curve up in a certain way, and you're saying that you derive the actual angle by which it curves using your principle of least constraints?
Yes, the common idea is minimization under constraints. The fluid in a tube is constrained by the walls of the tube, and I minimized the potential energy of the fluid system. Picture it as such. In my equation, we calculate the equilibrium between the forces that attract the fluid to its container and the force of gravity. If gravity were the only force, the fluid would be as deep as possible, Whereas if we set aside both gravity and the attraction to the container, then the fluid would take a spherical shape due to the attraction of the particles of the fluid to each other. Now, if the only force acting would be the attraction to the container, it would spread over the surface of the container, so that the volume of the fluid that touches the container would be at its maximum.
Okay, yeah, let me try to get this. So if I take a cup and put a straw inside of it, you're saying that there's three things acting on the water itself. You mentioned that gravity, the capillary action, and the attraction of the water molecules to each other. So if it was just gravity, then the water's barycenter would be at its minimum, whereas if it was just capillary action, that would look very different, which is called adhesion. And then if it was just the cohesion, then it would also look very different, probably like a sphere. Is that right?
Yes, the equation allows us to calculate these values. We represent values such as the volume of the water and the volume of the rest of the container. I don't know of this that you call a straw. I did also investigate the effects of other phenomena, such as friction.
Right, yeah, straws weren't invented yet at your time. We represent, but that's incredible. But your work in physics obviously extends far beyond just capillary action. You also made great contributions to, I believe, potential theory, right?
Yeah, here I used many analytical techniques such as integral transforms to derive new results. I also had my own manner of asking certain questions and applying these analytical techniques. For instance, in Theoria Attractionis, I encountered two ellipsoids whose mutual attraction due to gravity I sought to determine. The attraction of ellipsoids is more complex than it is for perfect spheres. Instead of trying to solve directly, I showed that the initially arbitrary ellipsoids can be transformed into confocal ones without loss of generality. Here I was able to avoid certain divergent series which occur in earlier proofs.
Okay, right. Okay, so ellipsoids are like spheres except a bit elongated, like basically 3D ovals. And you mentioned that you solved this using confocal ellipsoids instead of regular ones, which confocal ellipsoids are ellipsoids that share the same focal points. And I'll have a link to a video by someone called Steve Stein, which does a much better job explaining this than I can. The concept is usually covered in pre-calculus, actually. So you use this to calculate the attraction between ellipsoids as opposed to perfect spheres. And I think in any case, it's a bit difficult to visualize, but what we can appreciate here is that you did approach the problem from a completely different perspective. Please continue with your work in potential theory.
Well, we have Coulomb's law, which calculates the amount of force between two electrically charged particles at rest, called the electrostatic force. I found that this law was very basic, governing all kinds of different potentials. So in 1832, I began to investigate the magnetism of the Earth. This had already been a point of interest to Alexander von Humboldt, who tried to establish a grid of observation points all over the globe. The potential gain from such observations cannot be understated, as it could tell us about the distribution of terrestrial magnetism, local and temporal changes in its intensity, and declination and inclination. A comprehensive theory of terrestrial magnetism.
Wow. Yeah, and I think most of us are familiar with magnetic declination being the difference between true north and magnetic north. And then there's also, you mentioned declination, which if we I believe I should have something up on the screen here, but essentially like we take the Earth and we have the magnetic lines, then for some point on the other surface, the declination is going to be the angle of the magnetic line. So like by the equator, it's almost vertical. And then as you go towards the pole, it sort of angles like this. Now, in modern times, like here in the United States, we have, for example, agencies like the National Oceanic and Atmospheric Administration, which publish these kinds of values. Yeah, and you probably didn't have anything like that, right?
Oh no, we did not
Obviously.
possess anything like this, which made the endeavor all the more prudent. I wrote 3 papers on geomagnetism, and I shall explain my contributions. I defined terrestrial magnetism as the force which pushes a magnetic needle into a certain direction. I gave the magnetic potential V in an equation into which one must enter the magnetic flow at your position and the distance from the magnetic pole. Now, we must understand what the prevailing theories of geomagnetism were at the time. You see, it was assumed that there was a single magnet in the center of the Earth, or 2 separate magnets somewhere in the Earth's interior. I defined the magnetic poles and showed that there can be only 2 of them. This was not new knowledge, but I made clear the reason for only having 2 magnetic poles. As for my novel contributions, I provided a theorem which concerned the determination of the intensity of the horizontal component of the magnetic force, together with the angle of inclination which characterizes the magnetic field.
Right, and so here we can see that those are these magnetic field lines that I have.
Indeed, I showed that one may calculate the western component of the magnetic intensity from its northern component if only the latter is known for the surface of the whole Earth. The reverse is true with the additional condition that the northern component is known for at least one connecting curve between north and south poles.
Right, and so in the world magnetic model, there's several different components to the Earth's magnetic field or magnetic intensity. So just like how you have in regular Cartesian coordinates, if you have some kind of vector, then it has a like a vertical component and a horizontal component. So same here, we have like north-south component to a magnetic field line and an east-west component to it. So it's a vector quantity. It has its components in the x, y, and z directions. And you mentioned that you were able to calculate one component from another, which, it's interesting to note, but it shouldn't be surprising at this point that we can calculate these in Gausses. Although nowadays we do generally report them in microteslas. So how exactly did you determine these results?
Well, one more concept I want to explain is that while we can calculate the east-west or x component given the north-south one, the reverse is also true. That is, we can calculate the north-south component given the east-west one, but under the condition that the northern component is known for at least one connecting curve between north and south poles. I obtained these results by expressing the horizontal components as functions of the geographic longitude and latitude. Here, the lack of symmetry is explained by the fact that the meridians run into each other in the North Pole. I was able to calculate the vertical component of the magnetic potential by expanding it into a power series with respect to the reciprocal radius of the Earth. I then had spherical functions which depend on the assumption that the source of magnetism is located in the interior of the Earth. Then the vertical component is simply a function of the distance from the surface of the Earth.
Okay, yeah, I don't think that we need to go into too much detail for this formula, but what you're saying is that, so let's say I have the north-south component of the line, and I want to calculate the east-west component, I can do that. But then if I have it the other way, like I have the east-west component and I want the north-south one, then I need at least one other magnetic field line. So if I pull up a map of these magnetic lines that we have here, I would need to already have one of these first. And to actually get these components, you mentioned that it's a function of the distance from the surface of the Earth. Yeah, that makes sense because, like, the Earth's magnetic field extends pretty far. In fact, it even goes all the way up to, like, the Van Allen belts, which the Apollo astronauts, of course, had to take into account and make sure they avoid the highest areas of magnetism. And this is incredible because, like, this is what allowed us to get a full world magnetic model, which I'm reading here on the National Centers for Environmental Information. It's the standard model for navigation, for attitude, for heading systems that use the geomagnetic field. I mean, of course, GPS will tell you, like, your position, but pilots and navigators, they still use compasses because you need to get your orientation with respect to the Earth. And they use these models to navigate. So, Professor, did any like practical applications come out of this in your time?
As far as the non-theoretical results are concerned, I was able to use my theory to calculate the location of the magnetic South Pole. In 1841, Captain Wilkes, the American explorer, reached it at a point very close to where I had predicted.
Wow. Well, I mean, given someone who actually was able to predict where a random rock in space was going to be based on a few glances in astronomical terms, I suppose that, getting something on the Earth might even be easy in comparison. Although, no. Is there anything that you can say on geomagnetism? This is incredible.
Well, I also contributed to magnetism in general, not just on the Earth's magnetism. I gave the definition of an absolute measure for magnetic force. I used as a starting point that the magnetic fluid can only be described by its effects. I defined the unit magnetic fluid as a force of such strength that it repels another unit magnetic fluid at a distance 1 with intensity 1.
Right, okay, yeah, you say magnetic fluid, although I believe that we currently call it the magnetic flux, and it measures the amount of magnetic field that passes through a surface. And while the unit that you defined, the Gauss, is actually not used very often anymore, more or less being replaced by the Tesla, it still marked a very important step into getting an actual unified system of measurements for electromagnetism. So what kind of observations did you perform to test and develop your theories in this regard?
Not all, but much of it was with Wilhelm Weber. In 1831, Weber joined the faculty in Göttingen as a professor of physics. I had first met Weber in 1828 at the annual convention of German scientists and physicians in Berlin. He was the one who encouraged me to explore the natural sciences, and it was with him that many of my physics experiments were done. My first observations were naturally concerned with the local declination at Göttingen. Me and other scientists tried to gather information about the local, global, and temporal changes in magnetism. I say temporal changes because, in fact, we previously did not even know that the intensity of the magnetism changed with time. Humboldt established a calendar for the observation which determined the dates for the systematic measurement of the magnetic declination by as many stations as possible. Later, I was put in charge of this effort. My work led to the establishment of a magnetic observatory, a society with a journal, and an atlas of geomagnetism.
Those are impressive achievements indeed. But was this the same observatory as the one in Göttingen for astronomical purposes?
No, the magnetic observatory was different from the astronomical one, although it was next to it. I had designed it in accordance with Humboldt's observatory in Berlin. We did have to ensure that it did not contain any iron, which would interfere with our measurements. We also had to avoid drafts, so all the windows and doors shut very tightly. I tried to improve on the methods that Humboldt utilized. His measurements lasted 44 hours, which I was able to substantially reduce.
Wow. Just another achievement just to top off a list of amazing achievements in quite an incredible life. I mean, I think we could talk here for hours, and I think we've covered a lot of the specific areas that you contributed to. Life is clearly one of immense achievement, and this is in a time of great achievers. I mean, your contemporaries were people like Legendre, Lagrange, Bolyai, Riemann, and even among them, you clearly stood out as just quite a force of science and mathematics. Like we've seen the Wikipedia page of things named after you. We've gone over physics, we've gone over astronomy, we've gone over number theory. Truly something of like a 19th century Renaissance man here. Professor, thank you so much for joining us here in 2025 for this interview. It's truly an honor to have you here.
It has been an absolute pleasure talking with you as well, Kareem, and it's so interesting to know that my work has not been in vain. I'm so happy that you are still using my calculations and my formula, and that it has led to even more discoveries. So thank you also for having me. Dankeschön.
Thank you so much.